Hi again, everybody, and welcome back. You might remember from the last video segment how we were talking about moment of inertia, and how moment of inertia is really a description of how mass is distributed around a center of rotation. Now, I'm going to get to this table in just a minute right here, but real briefly, I'm just going to step back and go to a previous page in our notes that I referred to before, and that's this one right here, or moment of inertia. And remember how I described that moment of inertia, this capital I right here, is the sum of all these different masses that are all at different radii from the center of mass. Okay, so this little mass piece right here is a certain radius. This mass piece over here might be the same mass, but maybe 2 or 3 times the radius. This is the same mass, but a different radius, etc. So depending on the shape of the object, it's going to have a different moment of inertia. This weird shaped brown thing right here, whatever it is very different from, say, I don't know, example 1012, where we had a grindstone, where it was a cylindrical object with a very constant radius. And all this mass that was in the grindstone was distributed kind of evenly, or at least symmetrically, around that central axis of rotation right there. What we're going to start talking about in this segment is and this is going to be a table you're probably going to want to refer to, and that is moments of inertia for various different objects that are rotating. Okay, so remember, our moment of inertia for any object is I equals mr squared. All right, but depending on where the mass is in around that object. Well, actually, you remember that when we had that the baton, the two batons with the masses at the end. The one had I think 2 times the moment of inertia as the other one. So whether the object is rotating in the middle, like a rod or a baton, or rotating around the end, it's going to give us a different moment of inertia. So let's just go real quickly down a list right here. So if you've got a cylindrical or hollow shell, a hoop, all right. Well, where's all the mass right here? All the mass is not centered near the axis of rotation, which, by the way, there is no mass right there at the axis of rotation. It's hollow in there, but the mass is all distributed at some distance r from that axis of rotation. As such, the moment of inertia is simply going to be regular old mr squared, because that all these masses here, 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 here. I'm doing a bad job of this, but all around, well, that's really bad. All around the edge of that rim are going to be what make up the mass that has to be rotated around. Okay, compare that now against a solid cylinder or a disc right here, and you see that your moment of inertia, your I, is going to be 1/2 that. And think about that for a second. You've got 1/2 of the resistance to motion. You've got 1/2 of the mass. Now it looks like there's more mass right here, but what we're saying here is that if all masses are equal, all right, all these m's are equal right here. So here all the mass is distributed around the edge. Here all that same mass is actually distributed around the edge, but also towards the center as well. So much more of the mass is actually at a smaller radius than the mass right here. So you've got some mass at a full radius, some mass at a small radius, some mass at no radius, because there's some right in the center right there. So that means that moment of inertia for a solid cylinder is going to be 1/2 mr squared. Again, we're not going to go through the derivations of how these come about, but it's really by adding up all the different little mass pieces that are all at different radii from the center of rotation. Here, all the mass, right here, sorry, all the mass is at a constant radius. Here, all the mass is kind of distributed from the edge all the way to the center, and so 1/2 mr squared is going to be a solid cylinder. What if you've got a solid cylinder but that is being rotated on its edge? Okay, so say you put like an axle right there, and it's being kind of rotated around kind of that way. All right, well, 3/2 mr squared would be our moment of inertia for that. What if we have a long, thin rod? All right, long, thin rod. Now, this is actually slightly different than our batons, because remember, we assumed that our batons had mass on the end right here and here, but that the rod itself was negligible. Well, here, this moment of inertia calculation is actually accounting for the mass of the whole rod all the way through. And so, our moment of inertia would be 1/12 ml squared. What do you think L stands for? Length, right? The length of the rod. Just indicated right there. Okay, so the whole length, 1/12 ml squared. You would think that would be much less than if you had an axis at the end of a rod and you're swinging it around at the end, and it is much less. 1/12 is certainly much less than 1/3. But if you've got a long, thin rod and your axis of rotation is at the very end, it's going to be 1/3 ml squared. What if we've got a sphere, a hollow sphere, where again, very much like this hollow cylinder right here, all the mass is distributed around the edge. Around the edge. Oh, that's terrible. Of that sphere. Well, that's going to be 2/3 mr squared. All right, 2/3 mass times that radius squared. If you've got a solid sphere, it's going to be less. 2/5 mr squared is going to be our calculation for moment of inertia for a solid sphere. What if that solid? By the way, that's if the axis of rotation is assumed to be in the middle. What if you have a solid sphere and the axis of rotation is at the edge? It's going to be 7/5 mr squared. So that all this mass right here is kind of being rotated around that that axis of rotation. So it's going to be a higher moment of inertia. And we've got these two plates now, a solid plate. So what if the axis is through the center of the plane of the plate itself? That would be 1/12 ml squared, and L being the that length of that side right there. And so it's sort of spinning towards us, front to back. But if you have the axis going through a plate, through the plane of the plate, perpendicular to it instead of along with it, you have to deal with the width and the length. And we can't assume that these are going to be all squares. So the width and the length might be different. And so that's going to be, our moment of inertia is going to be 1/12 m times L squared plus W squared, length squared plus width squared. So these are all the different calculations for moment of inertia for various different objects. And you are by no means going to have to memorize all these. These will be available to you if you need them. But you'll probably want to bookmark this this segment or at least this page in your notes so that you can refer back to it, because you're going to be asked to know, well, not to know, but to look up the moment of inertia for various different objects, because we have different objects that we're going to be calculating the kinetic energy of. One last little thing before I close out this segment, and that is, let's look at the Earth. And we all know that the Earth is a solid sphere, but it's got an interesting moment of inertia. Partly because it is a solid sphere all the way through, or at least a spheroid, very close to a sphere. But that, if you remember anything from Earth science, if you ever took it, the various different materials that make up the Earth, well, it's hard to see my red dot in there, have different densities. They have different masses. So this orange stuff right here around the edge is it's very dense, dark rock that we call peridotite, just for your information. The lighter yellow stuff is, well, we think it's an even denser rock, but they're both rock. But as you get into the center right here, the core of the Earth, this sort of lighter yellow, is actually believed to be iron and nickel. And iron and nickel aren't even rock, but they're metal, and they're very, very dense. And the densest part of the Earth is the very center. That white spot is believed to be liquid iron. It's believed to be solid iron and nickel. So all that to say, even though the Earth appears to be you might say, a homogeneous sphere that is the same all the way through, it actually isn't. And so calculating the Earth's moment of inertia is a little bit more complex, because we have different densities going towards the center. So what we probably have to do is calculate the moment of inertia of all these different layers of the Earth and then add them up together. That's just one little earth science tie-in to moment of inertia. But that's going to be it for this segment right here. In the next segment, we're going to be looking at the kinetic energy of a rolling object as they roll either on a flat plane or down a hill or down a ramp. So that's going to be it for now. Thanks for following along. I'll see you on the next one.